Good morning, everyone. I'm sorry not to be there with you online for this conference, but due to Storm Bara, we had to go on the field to measure the consequences for the beach after this storm. I'm sure you will understand. For those who are not familiar with the study site, we are in the southeast coast of Northern Ireland. So the site is facing the Irish Sea. The study site is Dundrum Bay, which has semi-diurnal tides and meso to macrotidal range. The area is characterized by low wave energy, low to moderate, due to the restricted fetch of the Irish Sea. The wave direction is mainly from south, with storm direction occurring not just from south, but also from south-southwest and south-southeast. The shoreline analysis is focused on these two sides of Dundrum Bay, which are Newcastle and Ballykinler. In this part of the bay, in Newcastle and Marlow, we have a highly vegetated dune, and we have the same also on the other side of the inlet channel in Ballykinler. The two beaches are characterized by multiple intertidal bars, and the two sides are, let's say, divided by this inlet channel, which connects the outer bay with the inner bay, and there is this ebb tidal delta. So to study the historical evolution, geomorphic evolution of the site, we built a shoreline dataset. We also built a storm dataset to analyze the forcing parameters that cause the shoreline displacement. And we also collected some other data, like historical topographic profile of the beach. And we were also able to reconstruct the dune surface from historical aerial photos. We built a shoreline dataset starting from the Ordnance Survey maps from 1833. Then we also collected aerial photos from 1951 to 2020. And we also covered some recent gaps, for example, in 2019, with some GPS measurements along the two sites. For the storm dataset, we collected historical news from local newspaper from 1825. We gathered some hindcasted wave data from University of Cantabria and wave-watch tree models from 1948 to 2020. And we also collected recorded water levels from the Belfast and the Bangor tide gauges from 1901 to 2020. The dataset from the Belfast tide gauge was given by courtesy of Prof. Julian Orford. And regarding other datasets, we went to London to the National Archives because we became aware of a military operation that became publicly available, which was Operation Sandstone. So we were able basically to collect some topographic profile from the 60s and also some qualitative description of the beach. So at the end, the storm dataset is covering almost 200 years. The shoreline dataset is covering 187 years. We didn't collect satellite images because compared to aerial photographs, they have a much worse resolution in terms of spatial resolution, of course. And then we collected other datasets from 1963, so for the last 57 years. I won't go through exactly all the technical calculation that we did to estimate the shoreline accuracy from each data source. You just may want to know that we take into account every known, possibly known source of error for each dataset, and you can notice how the shoreline uncertainty, of course, decreased from the historical maps from the 19th century to the most recent dataset. So we had basically one shoreline as an average every 7 or 8 years. As shoreline proxy, we use the dune vegetation edge in the foraging because it was the most recognizable geomorphic feature from every dataset. As the first result, so considering only the shoreline change from 1833 to 2020, we first of all identify some specific zone where the displacement was greater. You can see from the net shoreline movement and the endpoint rate how the 19% of the shoreline in Marlog had a retreating trend in the last 2 centuries, whereas in Ballykinler, the 86% of the shoreline had an advancement trend. So basically, this tells you that the sediment, the sand, is mainly moving from Marlog to Ballykinler. Going more into the details of the shoreline change, so focusing on each period, you can see how in the older years, in the years covered basically by the historical maps, most of the displacement occurred close to the inlet zone. It was mainly related to the generation and growth of this sand spit here. And there was the generation of a very large blowout. From the 1951 aerial photos, we have seen a fore-dune retreat of more than 130 meters. If you go to most recent years, from 1951 to 2005, you can see that other 2 blowout zones were generated, and the blowout zone 3 was basically recovered almost entirely. You can also see how the size, so the inland retreat, is greater the more you go toward the inlet zone, so toward here. And you can also see, especially in most recent years, how the blowout zone, once generated and activated, they can recover, but they can also be reactivated from time to time. A peculiar erosive sign was left by the winter 2013-2014, which is this pink line here, where the 2 blowout zones, zone 2 and zone 3, were reactivated. But there is also this widespread retreat sign connecting basically the 2 zones. If you move on the other side of the inlet channel in Ballykinler, you can see how in the oldest years, so the years covered by the historical maps, again, most of the displacement occurred very close to the inlet zone, in the inlet zone 2, where there was a huge advancement from 1859 to the start of the 20th century. And then you can see a huge blowout generated and visible in the 1951 aerial photos. So again, how it happened in Marlog, where there was the generation of this huge blowout. Also in Ballykinler here, we had this blowout generation. Through more recent years, you can see how the inlet zone 2, where the blowout was generated, actually recovered multiple times, and the advancement continued also in most recent year. The rest of the beach, especially in most recent years, experienced an advancement widespread all over the beach here. Going again more into the details of the shoreline change, in Marlog and Newcastle, you can see how the only feature which is growing is the sand spit, even though in most recent year, the advancement almost stopped, so the geomorphic feature is quite stable. The rest of the beach is not experiencing a huge erosion. What is very clear is the generation and the recovery, and then also the reactivation of these blowouts. You can see the 3 lines that are representing the 3 blowout zones. After first generation of the blowout can recover, that can be reactivated and recover multiple times. In Ballykinler, in frame C, you can see that after the only single blowout generation, there was a recovery that continued also in recent years, where this area is actually advancing at a faster rate if compared to the rest of the beach. So this is a visual example how a blowout was generated, visible in the 1951 aerial photos. You can see how then the blowout, so the vegetation line, basically recovered. So talking about this, the forcing parameters, you can see in the first frame here the number of storms occurred between each period. The period have of course a different length, a different duration, because the temporal duration is given by the data source available to digitize the shoreline. You can see in frame B the cumulative storm energy expressed as the storm power index by Dolan and Davis 1992. And you can see the same cumulative storm energy normalized for the entire distribution of storm energy from 1948 to 2020. In frame D, you can see instead the storm energy of a typical year for each period. We also look for news, especially for the older years, in local newspaper about damages or flooding. We noticed some confirmation from the newspaper. We also found some confirmation by paper from O'Brien Ali in 2018, and from Orford and Murdy in 2015. Quite crucial was the winter 2013-2014 with this group of storms, which caused that retreat sign in the foreground I showed you before. Talking about the extreme water levels, which is maybe the most useful forcing parameter here, you can see on the left axis the extreme water level in meters, which refers basically to this black line. Instead, the right axis refers to the event duration, which is represented by the colored columns. These events are basing on the 30 top events recorded by the Belfast tide gauge, and only the years from 2011 to 2020 are referring to the Bangor tide gauge. If you remember, the larger retreat occurred in 1951 and 2014, and you can see also how these two dates were preceded by 3 consecutive extreme water levels events. So in particular, in 1946, we had 3 extreme water level events, and in 2014 as well. The topmost event was recorded in 1991, but there is an asterisk here because the tide gauge in Belfast was flooded and stopped to work, so we don't have the actual duration of the event. The second topmost event was recorded in 2014, and the third highest event was recorded in 2002. You can see how these last 2 events are in a return period comprised between 100 and 200 years, and they occurred less than 15 years apart. So in the last basically 30 years, we had the 3 highest extreme water level events. So of course, the shoreline analysis we did doesn't take into account the third dimension, so the elevation. So you can see that nowadays the beach, for example, in front of the golf course in Newcastle, is protected by some rock armoring, which is stopping the sand displacement, the sand dynamic between the dune and the beach. But you can see also how the beach surface decreased from the past. And of course, the shoreline analysis in the foredune doesn't take into account the elevation. So like in this case, you can see how the vegetation edge doesn't necessarily correspond to the dune base. So to improve this aspect, we built a new application of the structure from motion technique to reconstruct the 3D surface of the area from the older aerial photographs. We took the 1963 aerial photographs because they were the best in terms of overlap between the photos. And we basically applied the same technique that is nowadays used to reconstruct the 3D models, the digital surface models from drone images, for example. We published a paper in remote sensing about this technique, and we basically retrieved the 3 coordinates from a recent LiDAR with a very high spatial accuracy. We then compared the 1963 aerial photo with a recent orthophoto, and that was the way we identify ground control points that did not experience so much change through the years. So we basically were able to calculate the volume change from 1963 to 2014. And you can see how in Newcastle, Marlow, the sand lost was about 2,600 cubic meter from 1963 to 2014. On the other side of the inlet channel, there was a gain, which was twice the sand lost from Newcastle. As a sort of validation of this volume change, we digitized the historical topographic profile of the beach that we retrieved from that military operation. And we can see that also from that dataset, the beach surface in Ballykindler is nowadays much higher than the beach surface in 1963. There is more than 1 meter of difference. In Newcastle, on the other hand, the beach elevation remained more or less the same, even though nowadays we couldn't go further seaward to see how the beach profile is in the submerged part. So in a very simplistic way, the sand is basically going from Newcastle to Ballykindler. Of course, there is a ebb tidal delta in between, an inlet channel that is moving, so we need to understand how this geomorphic element is affecting the entire sediment dynamic of the bay. In Marlow, the foredune retreat is worsening, especially in the area close to the inlet. In Ballykindler, instead, the foredune is advancing, and there is a confirmation about this beach growth also in elevation from the historical dataset from 1963. In Marlow, the foredune are characterized by 3 areas of generation and reactivation of blowouts. So we have seen how they can be reactivated from time to time, but also how they can naturally recover. The sand speed is quite stable in recent years, but it may cause further shifting toward east of the inlet channel. And this will cause probably further erosion, further retreats in that part of the Ballykindler area. The volume gain in the foredune in Ballykindler is twice the volume lost from the foredune in Marlow, so part of the sediment is probably coming also from other areas, probably the ebb tidal delta, or probably also from submerged areas in the bay. We also have seen that cluster of storms and extreme water level events combined together are believed the main cause of the major retreats in the foredune, rather than the effect of single storms. With this, I'm concluding. Thank you all for listening, and I just want to let you know that the entire research was funded under the Interreg project MARPAM.